Okay, we're going to focus on Vz. So I'm going to declare that Vz is equal to 2000. Okay, and then we know that once we have Vz, the axis of interest is going to be YY. Okay, so this is our YY. So if it's Vz, things seems to be very convenient, right? Okay, so we know that this is our terminal, or we design our shear flow, major web. Okay, and then we have this terminal, terminal 2. It can be going out or coming in, does not matter. Terminal 3 and terminal 4. So this is the design of your shear flow. Okay. So you can see if it's Vy, a lot of points are 0. We know that point A is 0 because at the terminal. Point E is 0 because the second moment of area is also at the terminal. Point D is also equal to 0 because of what? Because it is because the first moment of area is also equal to 0, right? So it's not complicated at all, I hope. Okay, so now we know that the formula we're going to use is the shear stress is equal to Vz over Iyy, right? Qy over T. Okay, so again we need to find Iyy. So we know that Yy, this is our width, and then this is our depth, like how we like how we learn from, what is it, like how we learn in, I'm lost of words now, buckling, okay, or bending moment. Okay, so the width is again 1.25 multiplied by 1.25 power 3 divided by 12 plus or minus, right? The width is equal to what? 1.25 minus by minus by 0.125 twice. Okay, because you have left and right. And then the depth, okay, the depth you have twice, okay, 1.25 minus by 0.125 minus by 0.125 divided by 2 cube. Okay, so this is equal to 1.25 times 1.25 power 3 divided by 12 is equal to 203.451 times 10 to power minus 3. Let me do again. 1.25 times 1.25 divided by 12. Okay. Minus, so 1.25 minus 5.125 minus 5.125. So there's a width 1, or twice of 1. And then the depth is 1.25. Hey, what am I doing now? No. The first one is 1. And then 1.25. I think the cube, this is the cube now. Okay. So 1.25 minus by 0.125 minus 0.125 divided by 2. That's by 2 is 2.125. And then divided by 12. Let me see. So the width 125. Yep. The depth is 2. No. The depth, I got it wrong. Sorry. This is 2.5, right? The depth. Okay, 2.5. Wait, what is the depth? Okay, 2.5. Wait, let me. I'm having issue with the depth. Okay, I know the whole thing divided by 12. So the depth is 2.5, right? Minus by 0.125 times 3. Then cube. Yeah, that's more like it. So 1.25 minus 0.125 minus 0.125, that's 1. 2.5 minus by 0.125 times 3. So 2.12. Oh, it's the same. Silly me. So this will be equal to 203.451 minus by 2.125 power 3 times 1 divided by 12. So it's equal to 799. Hey, the width, I'm not getting it now. So 1.25 power 4, 203.451. Okay, so 1.25 minus 0.125 minus 0.125. Eugene, really sorry, people. My bad. 2.5. So that's the width. Okay, so 2.5 minus 0.125 minus 0.125 is equal to 2.25. Okay. Did I do Eugene? Really? My bad, it's late. Okay. So 2.5. None of you are correcting me. I'm sorry, people. 2.5 power 4 divided by 12. That's more like it. 3.255. So 2.5 power 4 divided by 12. 3.2552. So 2.5 minus, yep, this is correct. Yep, so 2.5, 2.5 minus by 3 times by 0.125, 2.125. Now we get more realistic value because it cannot be a small number minus a big number, something's wrong. So 2.25 minus 2.125 power 3 divided by 12 is equal to 1.7992. Okay, so this is equal to 3.225 minus 1.7992 is equal to 1.4258 inches cubed. Let me do it again. Yep, 3.2552, 2.25 times by 2.125 power 3 divided by 12, 1.7992, 3.2552 minus 1.7992, 3.2552 minus 1.7992, 1.456. What am I doing? Okay. Yep. Okay. So from here, you know why. So you already can declare that the shear stress at point A is equal to 0. This is because Q is equal to 0. The shear stress at point D is equal to 0 because Q is equal to 0. The shear stress at point E is equal to 0, Q is equal to 0. Now for this case, this is because it's at the what? Terminal. This is also at its terminal. Okay. So now we want to find the shear stress at point B, right? So the shear stress at point B, it starts from this terminal. The area of interest is this entire area now. So we know that this is a box beam analysis. Okay. So at point B, we have our box beam analysis. And then what we have is we're going to have 2Q. Okay. So the width, so the shear second moment, first moment of area about y-axis at point B, the width is equal to 2.5. The depth is equal to 0.125. The y bar is 1.25. Okay, 1.25 minus by 0.125. So this will be equal to, the width is 2.5. The depth is 0.125. The y bar is 1.25 minus by 0.125 divided by 2. Come on, Eugene, wake up. This is, give me another 1 minute, okay? I think I'm done. So 1.25 minus by 0.125 divided by 2 times by 0.125 times by 2.5 is equal to 371.094 times 10 to the power minus 3 inches cubed. I do it again, 1.25 minus 0.125 divided by 2 times by 0.125 times by 2.5. 371.094, right? So the shear stress, so is the intersecting plane is X and the direction is in Z, no, in Y, right? No, it's in Z because at point B you see it's in Z at point B. So 2000 divide by 1.456, and then you have 371.094 box beam 0.125. Okay, so this is equal to 2000 times by 371.094 power minus 3 divided by 1.456 divided by 2 divided by 125 is equal to 2.038, 2.039 times 10 to the power 3 psi. Okay, let me check. 2000 times by 371.094 power minus 3 divided by 1.456 divided by 2 divided by 125. Okay, I will continue again tomorrow for the last point, and then we're going to do more examples. I'll see you guys tomorrow. Thank you for your time. Thank you for your attention.